Assalamualaikum to our lecturer, Dr. Muhammad Shukri bin Zakaria. Today, my group will present about our project, CFD and FEA study of a branch angle pipe junction. Before we start, I will introduce my name and my group members. Firstly, my name is Amir Hakim bin Hairul Amri with diameter 40 mm. The second one, Muhammad Harid bin Muhammad Nurulizan with 50 mm diameter. And the third one, Muhammad Nasrul Haq bin Jamaldin with 65 mm diameter. And the next one, Muhammad Fakrul Hakim bin Muhammad Fuzi with 80 mm diameter. And the last one, Muhammad Shukri bin Muhammad with 90 mm diameter. Project overview. There is 5 different pipe diameter for my group with the inlet velocity 4 millisecond and with the same turbulent model. Background. Branch pipe junctions experience complex turbulent flow when two inlet streams merge, generating recirculation zones, non-uniform pressure distributions, and stress concentrations at the geometry discontinuity. So, our project have a few objectives. The first one, simulate turbulent water flow, which is CFD, in ANSYS fluent. The second one, evaluate velocity and pressure fields for 5 pipe diameters. The next one, transfer CFD pressure to ANSYS mechanical one-way FSI. Furthermore, analyze total deformation and von Mises stress. And the last one, compare FEA stress with analytical Barlow-Hope stress. That's all from me. Thank you.
Our methodology consists of 4 main stages. The first is the geometrical design. We created a Y-shaped branches model pipes with a constant wall thickness of 3 mm and branch angle between 40 to 90 degrees. The second stage is mesh generation. We generated a lateral meshing with 5 inflation layers near the wall to improve the boundary layers resolution. 3 mesh levels were tested, which were coarse, medium, and fine. The third stage is a CFD simulation. We used the SSTK omega turbulence model because it provides the accurate predictions. The separated flow and wall bounded turbulence. Water entered to 2 inlets at 4 meters per second, while the outlet pressure was fixed at 0 Pascal. Finally, the pressure distribution for CFD was imported to ANSYS Mechanical. The pipes ends were fixed and we calculate the total deformation and von Mises stress. Before analyzing the result, we performed the grid independent test to ensure the machine quality did not significantly influence the simulation outcome. This slide shows the several stages of CFD simulations. The first image illustrates the generated CFD mesh. The second image presents the contour plot, which shows the pressure and velocity distribution inside the pipe. The third image shows the path line or streamlines that help us visualize the movement of water through the branch junction. This streamline clearly shows how the two inlet flow merge together before entering through a single outlet. The complex flow pattern also indicates the presence of vorticity and recirculation region near the junction. This visualize help us understand where the pressure and the flow separation occur before performing the structural analysis.
Assalamualaikum, my name is Muhammad Fakrul Hakim. Today I would like to present about mesh generation and grid independent test. For the mesh generation and grid independent test, the goal of this analysis was to ensure that our simulation results are accurate and independent of the computational grid density. We test 5 different geometric diameters ranging from 40mm to 90mm across coarse, medium and fine mesh configuration. As you can see in the data table, as we refine the mesh from coarse to fine by increasing the number of nodes, both maximum pressure and maximum velocity begin to converge. For example, looking at the 50mm, the pressure drops slightly from 34,340 Pascal to 32,800 Pascal. The maximum velocity stabilized from 8.949 meter per second down to 8.911 meter per second. Our established criterion for converge was a less than 5% change in key output when moving from a medium to a fine mesh. Across all test diameters, the variance between the medium and fine configurations fell well within this 5% limit. Moving on to our CFD flow analysis result shown in the slide. On the top left chart, you will see the maximum outlet velocity range between 8.9 and 9.8 meter per second across all diameters. Because our inlet velocity was 4.0 meter per second, fluid continuity naturally forced the combined flow into a single outlet, causing the peak velocity to more than double due to a non-uniform profile. Looking at the bottom left chart, wall pressure remains steady at around 33 to 34 kilopascal for the smaller diameters. However, as the diameter increased to 80 and 90 mm, we see a sharp rise in peak stagnation pressure, jumping up to 40 and 41.5 kilopascal. This peak static pressure occurs right at the outer inlet walls near the junction node. This behavior is driven by two main aerodynamic phenomena highlighted on the right. First, the abrupt 90-degree geometric change causes flow separation, creating a low velocity recirculation zone on the inner outlet wall. Second, this sharp turn generates strong secondary flows, specifically the vortice, which spiral several diameters downstream before decaying.
Transitioning from fluid flow to structural response, we conducted a finite element analysis across all 5 pipe diameters. Our result shows a clear linear relationship for every 10 mm increase in diameter. The maximum stress rise by approximately 13.3 kilopascal, with the 90 mm pipe peaking at 105 kilopascals, while information remained minimal in the range of 10 to the power of -7 meter. The junction node is consistently the most critical region. This is where geometric stress concentration meet non-uniform pressure loading from fluid structure interaction. Crucially, however, our calculated stress is still vastly lower than material yield strength of 250 megapascal, with a factor of safety exceeding 2000. Across all cases, we can confirm the junction is structurally rock solid under this operating condition. Now, let's look at our result held up against industry standard method. To validate our structure model, we benchmark our FEA findings against the Barlow-Hoop stress formula. What we discovered is a significant discrepancy. The analytical Barlow formula consistently overestimates stress by staggering 70 to 80% compared to our simulation. For example, in our largest 90 mm case, Barlow predicts a stress of 525 kilopascals, while our FEA results sit at just 105 kilopascals. Why the gap is so large? It is because the analytical formula assumes a uniform pressure on a perfect straight cylinder. It cannot see the localized stagnation zone we identify in our CFD, nor it can account for the geometric discontinuity of 90-degree branch, which introduce complex bending moment. This comparison highlights a vital engineering takeaway, where Barlow is useful for straight section. High fidelity FSI FEA is not negotiable for designing complex junction where flow dynamic dictate the load.
Assalamualaikum. I'm going to talk about conclusion. First conclusion is CFD finding. The first conclusion is outlet velocity times 2 inlet due to mass continuity. Next is highest pressure at stagnation region outer inlet wall near junction. Third one is 80 mm and 90 mm, 25% higher peak pressure than smaller diameter. Next is din vortice observed downstream secondary flow persist several diameter. Now I'm going to give conclusion for FEA findings. The first conclusion is junction is always at the critical region, geometric stress concentration. Max stress increase 13.3 kPa per 10 mm diameter increase. All FOS more than 2000, structurally safe, well within elastic range. Barlow overestimate by 70 to 80% versus FEA, use FEA for junction design. Next is my recommendation. The first recommendation is use filtered tape junction and smaller branch angle. Like example for 45 degree to reduce stress concentration. Second one is scale wall thickness proportionally with diameter. Fixed 3 mm become increasingly thin at 80 and 90 mm. The third one is rely on FSI FEA for junction safety assessment. Barlow is valid for only for straight pipe section. The fourth one is inspect the outer branch for wall erosion. Din vortice accelerate material loss near the inner wall. So that's all from me. Thank you.